time for us to do some more practice involving the second partials test, which really means that we're going to spend most of our time, the majority of our time, is really about working with finding the critical points. 2 equations, 2 unknowns. Oh, what a beautiful sound. Because it really gives us a chance to really flex our algebra muscles. Woohoo! Now you're probably thinking like, oh, my algebra muscles, they're not really flex-worthy yet. Well, there's a way to get there. It's called practice. The more you practice, the better you become. And pretty soon you're just going to be walking down the street saying, look at my awesome algebra skills. I'm the best. I believe in you. I know you can get there. And you'll do it through practice. If you're following along with the video, make use of the pause button. See a problem? Try it yourself first. Get that extra practice in so that you too can become amazing. Well, let's begin. Our first problem. Find and classify all the critical points for the function f of xy is e to the y times y squared minus x squared. Now this one is probably going to be a little bit unusual for today because most of the time when we have a find and classify, we usually have polynomials. Not because it's restricted to polynomials, but because they're the easiest ones in terms of actually finding things. But that doesn't mean we can't do other things. We're pretty good, right? Of course we are. So let's try it out. Now the most of the work, the majority of it, is going to be in the find phase. And this is a really nice function. So when we talk about find, we're really talking about when does the gradient equal 0. Classifying doesn't work for any other kind of critical points. At least the second partials test, and that's where we're in right now. Okay, so away we go. So we start with our f sub x. Well, this is actually pretty straightforward, right? Because there's only one x. So it would be e to the y, which is this constant, times negative 2x. And how about f sub y? Well, product rule. So we take the derivative of the first times the second, and plus the first, e to the y, times the derivative of the second, which is 2y. And here we were taking the derivative with respect to x, so the derivative of e to the y with respect to y is e to the y. All right, great. Now between these two, certainly our eye drifts towards the derivative with respect to x because, very simple, it's a nice product of things. Remembering, what are we doing here? We're setting these equal to 0. And certainly, it looks a lot better to work with that. In fact, great news. Because remember, the exponential function is a really optimistic, outgoing, positive function. See, e to the y is never 0. It's always strictly positive. So if I have e to the y times minus 2x equals 0, it must be the case. It must be. There is no choice that x equals 0. Well, great. Well, what does that say? Well, now let's come down into here. What do we have? Well, notice we can factor the e to the y out. Great. Then we have y squared. X squared is 0. Gone. Then we have plus 2y equals 0. But again, e to the y can't be 0. So it says, look, it's the y squared plus 2y. That's what's causing the 0. And that factor says y times y plus 2. So we say, great. Y equals 0, or it could be negative 2. When we combine, we say there are 2 candidates, 2 places where we may have something interesting happen. There are 2 critical points, really. And they are at 0, 0, and 0, negative 2. Okay, so our critical points are 0, 0, and 0, negative 2. Well, that's only part of the story, right? Because we did the find, got to do the classify. Well, so we switch gears and we say, all right, the second partials test, that's what helps us do our classify. So time to take some more derivatives. We have f(x(x), taking the derivative with respect to x, would be minus 2 e to the y. Fxy, take the derivative here with respect to y, well, that would be minus 2x e to the y. Because the derivative of e to the y with respect to y is e to the y. And f y, oh my goodness, there's a lot there. Okay, what will that be? Well, let's just work through it. The derivative of the first, e to the y, times y squared minus x squared. Okay, derivative of the first times the second, plus the first times the derivative of the second, 2y, plus here, the derivative of the first times the second, 2y, plus the first times the derivative of the second. That's what we'll get. Now we can simplify this, right? Because we can say, look, we'll factor out an e to the y. Why not? Okay, then we're going to get y squared minus x squared plus 4y plus 2. And there we go. All right, well, great, wonderful. Now what? Well, the next thing for us to do is to test our points. So what does that mean? Well, we're going to have our d, which is fxx fyy minus fxy squared. So let's plug in. When we plug in 0, 0, what happens? So let's do a little computation, right? Now the nice thing about 0, 0 is it says what? Anything with an x or a y goes away. So notice the fxy term completely gone. Nice. All right, how about the fxx? Minus 2e to 0, that's minus 2. Now fyy, okay, well, that's e to 0, it's 1. 0, 0, 0, plus 2. Okay, so it's a plus 2. So it's a minus 2, a plus 2, and then we subtract 0 squared, and we say, aha, that's negative 4, which is negative. Of course, the fact that we said negative 4 gave it away that it's negative, which means that 0, 0 is a saddle. Okay, so that's the classification for that point. But wait, we still have another point. Okay, so what happens at 0, negative 2? Now, when we plug in 0, negative 2, let's just, let's do it. All right? So one way to get the answer is to do it. It's a very bold strategy. We'll see if it pays off. So, don't get too nervous about the fact we have e to the negative 2. We'll talk about that in a second. So, well, we'll start over here. Hopefully we have space. d0 of negative 2 would be what? Well, when we plug in 0, negative 2, we're going to get minus 2 e to the minus 2. That's fine. Now here, when we plug in 0, negative 2, well, we're going to get 4 minus 0 minus 8 plus 2. Right? So 4 plus 2 minus 8 is a minus 2. E to the minus 2. And when we plug in 0 minus 2 here, we'll get 0. Right? Because x is 0. Aha! Nice! Phew! That actually turned out to be not so bad. Of course, we're going to square it, but it doesn't really matter. Now, what happens? Well, we have a negative times a negative, which is positive. Perfect. So we know it's a local something. Now the question is, what something? It's a local fill in the blank, right? Well, for that, we look at these values here. And what do we see? Well, we see they're negatives. It's negative for fxx. In fact, we can see it right away. It's negative for fyy. So that says, aha, this has to be a local max. And we're done. We found our critical points, and we were able to classify them. Woohoo! Good. Nice. Nice. So this shows you the process works, right? It's all about just being patient. Take your partial derivatives, set them equal to 0, and solve. Life is good. Well, by the end of today, we're going to get a lot of practice. A lot of practice. We're probably going to get almost too much practice. Is there such a thing as too much practice? Probably, because we're about to do it. On to our next problem. Find and classify the critical points of the function 1/3 x cubed y squared minus 7x squared y plus 24x minus 9y. Oh, I think this one's going to be interesting. Well, let's begin. So, same process. Take the partial derivative, set them equals to 0, and start solving. So, if we do that, what do we have? F sub x would be, well, x squared y squared minus 14xy plus 24. And f sub y, well, 2/3 x cubed y minus 7x squared minus 9. Now, looking at this, our sort of first reaction is to say, the f sub y, it kind of looks like we could solve for y, but we'd have to do division by x, and it's just, we don't really want to divide by x. We could. We know for sure that there's no place where x equals 0 is a critical point. Now you're probably thinking, and how do we know that again, Steve? Just remind me. How do we know that? If x equals 0 ever were a critical point, look at the second equation. 0, 0 minus 9 equals 0. Can't happen. So we know x equals 0 is not a possibility at a critical point. So we could divide by x if we wanted to. But I don't want to. I don't want to, because I'm a little bit paranoid about what would end up happening if we pursued that. Let's look at the first equation, the f sub x. Now that one's a little bit interesting, because if you look at it, you have x squared y squared minus 14xy plus 24. Let's think about that. You notice how you have xy here, you have x squared y squared there. You could think of it as something like xy squared minus 14 times xy plus 24 equals 0, which means it looks like a quadratic because it's a quadratic. That's a good reason why it should look like one. If you wanted to, momentarily we could say, well, let's introduce this z squared minus 14z plus 24. I'm doing the classic mathematical maneuver called introduce a name to simplify things for a moment. So in this case, we're introducing the name z for xy. All right, great. Well, what do we do? Well, what we can do now is we say, it looks like a quadratic. Let's do what we do with quadratics, which is try and factor. So the question, can we find two numbers that multiply together to 24, but add to 12? Well, this one is a little bit interesting because 24 is very factorable. There's lots of ways to write it. Well, let's think. 24 and 1. No, that adds to 25. That won't work. 12 and 2. That adds to 14. That could work, right? Okay, so this looks like z minus 12 and z minus 2 equals 0. All right, good. Great, actually. Cool. So what does this help us decide? Well, it says, and you can check, by the way, that it does multiply out. You see that z squared, and you get a minus 2z minus 12z is minus 14z plus 24. So you get that z, which is really xy, is 12, or xy is 2. All right, so that's good. We actually were able to use the first equation to really simplify the relationship. And it's quite beautiful now. So let's go and dig into our f sub y. What can we do? Well, now let's think about this. What happens? We get, notice that there's only one y here. So I can really think of this as 2/3 x squared times xy minus 7x squared minus 9 equals 0. And so we're going to say, aha, see, I can replace that xy now because we have sort of two paths on which we get to travel down. So let's see what happens if we choose the xy equals 12. Well, in that case, I can replace this part by 12. 2/3 times 12, well, that's 8. So we get 8x squared minus 7x squared, which is x squared minus 9 equals 0. All right, well, that says x squared equals 9, or x equals plus or minus 3. Okay, so what happens? Well, if x equals 3, 3y equals 12, so that would say that y should be 4. If x equals negative 3, minus 3y equals 12, so y should be negative 4. So those are two critical points. So that's going down the xy equals 12. Now, what about the xy equals 2? Well, let's do it again. So if xy equals 2, what happens? Well, again, this becomes 2 times 2/3 is 4/3. So you have 4/3 x squared. Then we're going to subtract 7x squared. All right, well, 4/3 subtract 7. That's a dangerous computation. I'm going to write that one down because I feel like I might lose it if I try to do it all upstairs. But really, what is 7? 7 is 21/3. Take 4/3 and subtract 21/3. You're going to get negative 17/3 x squared equals negative 9. Or, whoops, plus negative 9 equals 0, sorry. But now, move the 9 across and multiply, you end up with x squared equals negative 27/17. You're like, wow, that seems complex. Well, you can't have a real number squared equal a negative. So that says, there are no solutions down that particular track. So even though, we say, well, potentially it could be the case that xy equals 2, and we went down and looked, we said, but there wasn't a consistent answer, at least as far as real numbers go, and in our class we're trying to keep it real. All right, great. So that says there's only 2 critical points. Beautiful. Nice. We started, we were like, wow, we're going to get a lot of critical points because that's a high power. No, just 2, but that's enough for us. That'll keep us busy. Well, let's finish up. What do we need? Well, we need to know what is fxx. Okay, so we'll come along. That's 2x y squared, and then minus 14y. fxy will be 2x squared y, and then minus 14x. And fyy, well, that'll be 2/3 x cubed. Okay, so now comes the part where we're very patient with our algebra. Okay, because what are we going to do? Remember, we have this discriminant, fxx times fyy minus fxy squared. And that's what we need to compute. So, well, let's proceed with a little sense of, let's say, caution. Okay, so when we plug in 3, 4, what will happen? Well, we're going to get 2 times 3, which is 6, times 4 squared, 16. 6 times 16 is 96. Subtract 14 times 4. Well, 14 times 4 is 56. So 96 subtract 56. Okay, that's fxx. How about fxy? All right, so we're going to get 2 times 9, because that's 3 squared is 9, times 4. Okay, so that's really 2 times 9 is 18, times 4 is 72. Okay, so that's 72. Subtract 14 times 3. Well, 14 times 3 is 42. All right, so 72 subtract 42. Whoops, got ahead of myself. That's the fxy. That's what we're going to put over here. The next term is the fyy. 2/3 x cubed. So that's 2/3 times 3 cubed. All right, well, that's 18. So that's what goes next. 18 subtract. Now I regret crossing that out, but that's okay. Remember, it's 2 times 9 times 4, which is 72, minus 14 times 3, which is 42. And that's going to get squared. Okay, well, what happens? Well, what happens, we get 96 minus 56, which is 40, and then we have 40 times 18. Well, that's 720. All right, here we get 72 minus 42. Well, that's 30. And then we're squaring it. So subtract 900. And that's a negative quantity. All right, great. Well, negative, we're done. That means saddle. Okay, phew. Now, what happens when we plug in -3, -4? And now we can actually save ourselves some work. Because see what happens. See, there's going to be 3 negatives multiplying together, which means we're going to flip the sign. Here there's 1 negative, flip the sign. So instead of 96 minus 56, it's -96 plus 56. Great. Here we flip the sign again. So instead of positive 18, negative 18. All right. See, because it's a negative cubed. And what about fxy? We flip the sign, right? Because it's negative cubed, and there's a negative. So subtract negative 72 plus 42 squared. But look, negative, negative, these multiply together, so they still end up with 720. And here, it's still negative 30 squared is 900. So it's still the same computation. 720 minus 900, that's negative. So in both places, both the critical points we got negative value for the discriminant, which means that both of these points are saddles. So they're both saddle points. Now you might say, wait, we can have multiple saddle points without having a min or max? Yes, we just demonstrated it. This is an example of a function which has it. Indeed, in some sense, we'll probably see saddles almost as often or more often than local mins or local maxes. It's very unusual to have functions with lots and lots of local mins and local maxes without having a lot of saddles as well. All right, well, wow, that one's pretty good. I will say, for the second problem in our set, usually they're not quite this interesting, but it's a good one to really get going. All right, well, let's keep moving. On to our next problem. So, find and classify the critical points of this function. Ooh, it's an h this time, which really doesn't mean anything. It's just a name. We don't really care what we call our functions. But 1/3 x cubed minus x squared y plus 18y squared minus 72y minus 24. Now, before we get too far, let's just point something out. Do you see that minus 24 on the end? What difference will it make? And the answer is, it doesn't make any difference. Which really isn't too surprising, because what is it doing in terms of the function? See, that's affecting moving the function up and down. But if I have a local maximum, so here's a local maximum, if I move up, it's still a local maximum. Or if I have a local minimum, if I move down, it's still a local minimum. And if I have a saddle, if I move it up or down, it's still a saddle, right? as I shift things around, I don't change the location of the critical points or the classification. So they could have put really exotic numbers in. So this is a way to test, are you paying attention? They might say, what's an exotic number? Something like e cubed, because you'd be surprised how many people have struggled to take the derivative of e cubed. Or maybe you wouldn't, I don't know. I hope it's not you. It's 0. All right. Well, we proceed like we normally do. H sub x. All right. X squared minus 2xy. Oh, that's nice. And no more x's. Okay, we're going to set that equal to 0. H sub y. Okay. Minus x squared plus 36y and minus 72. And we're going to set that equal to 0. Now, look at this. The first one, h sub x, looks great because we see it has this nice factorization going on. It says, we have x times x minus 2y equals 0, which means x equals 0, or, of course, it could mean x equals 2y. Well, let's just explore what this gives us. So suppose we start by saying, what happens if x equals 0? So we're looking down the first option. If x equals 0, we go into our h sub y. We say, okay, well, that means that term is gone. That would lead us to say 36y minus 72 equals 0. Okay, I can add 72 to both sides and divide by 36, which would say y should be 2. Now, remember, we're on the x equals 0 side, so combined with y equals 2, we get a point, 0, 2. All right, there we go. There's our point. Now, what if x equals 2y? Okay, so now we're going to go down the other option. If x equals 2y, we come down here and say, okay, well, replace x by 2y. So we get minus 4y squared, because that's what would happen if you squared 2y, plus 36y minus 72 equals 0. Well, let's make this leading coefficient 1. We like quadratic equations with leading coefficient 1, which means we'll divide by negative 4. So y squared minus 9y, and of course you have to think 72 divided by 4, it's 18. All right, so plus 18 equals 0. Okay, good. So, well, what can we do? Well, we're looking for ways that we can factor. Because it's a quadratic, we like to think it can factor. Are there two numbers that multiply together to give us 18, but would add to give us 9? Well, 3 and 6, I think that works. So let's check. Y minus 3, y minus 6. That would be y squared, good. Minus 6y minus 3y, ooh, minus 9y. And plus 18. Nice, nice. Okay, so that gets us to y equals 3, or, of course, y equals 6. Now, what if y equals 3? Well, x is 2 times y in this scenario, so that would correspond to the point 6, 3. And then, if y equals 6, x would be 2 times that, which would be 12, 6. So there are the other 2 points. So there are a total of 3 critical points. Ah, well, that was kind of pleasant. Kind of, after some of the more recent ones, almost too good to be true. Well, but no, we did the work. It's not too good to be true. It's just the right amount of true. All right, well, what are our other pieces? hxx. Okay, that would be 2x minus 2y. How about hyy? 36. Ooh, okay. By the way, at this point we can stop and say, not that stop with the problem, or just pause. We definitely can't have any local maxes. Can you see why? Look at hyy. What's true about hyy? It's always positive. Always positive. And so remember, when we're testing for local mins or local maxes, we can look at HYY. Since HYY is always positive, if we have a local anything, it has to be a local min. So there can't be a local max. All right, back to our problem. HXY, well, okay, minus 2x. Great, wonderful. So our discriminant is hxx times hyy minus hxy squared is, well, 2x minus 2y times 36 minus 2x squared. Okay, well, we're ready to start plugging things in. All right, so plug in 0, 2. Well, the good news is, look, you only need to pay attention to I guess you do have a y there. All right, the good news is it's not so bad, I guess, right? 0, that zeroes out, there's 0, and then we have 2 times minus 2 makes us a negative 4 times a 36 and minus 0 squared. Now, we could compute this and say, gross. That's right, 144, but negative, right? But we don't care about the 144-ness. We care about the sign. It's a negative value. So that tells us 0, 2 is a saddle. Great, great. All right, next point, 6, 3. Well, let's see what happens. Well, we're going to get 2 times 6 is 12, and minus 2 times 3, 6. So we're going to get 6. Okay, that's great. Times 36. All right, 6 times 36 minus, and now we have to say, okay, 2 times 6 is 12. All right, so it's negative 12 squared. Now, you might be like, what does that turn out to be? I mean, 6 times 36, well, we can work it out in detail. For example, 6 times 36 would be 216, and 12 squared, that's the gross, still 144. And then we could figure out very precisely what the number is, but we don't need to know the number precisely. We just need to know the sign. In other words, which one is bigger. You can think about it this way. Say, look, this is 12 times a 12. If I pull off a 2 and move it to the 6, I could think of this as 12 times 18. That's bigger than 12 times 12. But at any rate, this is certainly positive. It's positive, and notice our partial derivatives are both positives. We even made that comment before. So that says, hey, this point here, 6, 3, that's going to be a local min. All right, well, that leaves us with one more point. Okay, 12, 6. So what will that happen to be? 2 times 12 is 24, minus 2 times 6, which is 12, times 36. Subtract 2 times 12 is 24. That's actually negative 24 squared. Like, now what? Well, kind of can do the same reasoning. See, look, 12 times 36. Here's the reasoning. I'm going to pull a 2 off from here. So think of this as 2 times 18, and move that 2 to the 12. So this is the same as 24 times 18. And then I'm going to subtract 24 times 24. Now, can you see which one is bigger? 24 times 18 or 24 times 24? The 24 times 24 is bigger, and it's being subtracted. So, as a result, it's a negative value. I don't need to know the exact value. I just need to know the sign. I could stress out, and I could say, well, it's the same as negative 6 times 24, which is, I think, negative 144. Wow, this problem is really gross. That number keeps showing up over and over here. But the point is, I only need to know the sign. So the fact that this is negative, that says, hey, this other point, 12, 6, this is also a saddle. So 2 saddles and 1 local min. And there we go. That's it. Wow. Cool. Wow. What a problem. Now, you're probably thinking, boy, it would be great if we get to use calculators, right? Well, sometimes you get to. But even if you don't, just be patient. Just think about magnitude. What's bigger? How do you figure that out? All right, well, on to our next problem. Find and classify all critical points of a very long expression. 2/3 x cubed plus 2x squared minus x squared y minus 4yx plus a third y cubed minus 5y plus 7. Woo! Wow. Well, thank goodness we got a lot of paper here, right? So that we're not going to run out of space. We hope. We hope. All right. Well, let's begin. So we'll start by looking at our partial derivatives, f sub x. All right, just go through it. Take the derivative with respect to x. We'll get, here, 2x squared plus 4x minus 2xy minus 4y. Wow. Huh. Interesting. Okay, and we're going to set that equal to 0. Now, how about fy? Well, nothing. There's something. Minus x squared. There's a minus 4x. And a plus a y squared. And a minus a 5 equals 0. Okay, wow. Huh. What a problem. I mean, what makes it interesting? Well, you have these very long things, right? And it's not so clear, like, what do we solve for? You could say, well, I could solve for y squared. That's not a great choice because you don't have a y squared there. You can't really solve for x in either one. Maybe we could solve for y there. As they say, But looking at this, we might start to say, certain things start to pop out, especially in this first one. See how it's like the 2, 4, there's a 2, a 4. In particular, this feels very close to that. It's almost like you changed an x for a y, right? Maybe we can do something there. Let's think about it. What can we do? Now, one of the things we oftentimes look for is factoring, and one good way to factor is to sort of group things together. So if you think, well, let's just group the first terms and the second terms. In the first terms, you could factor out 2x. You have an x plus 2. In the second terms, we could factor out a minus 2y. And then what would we have? Well, we'd have an x and a plus 2. And then we're like, whoa, this is nice. Because they both have x plus 2's in them. In fact, they both also have 2's. So this becomes 2 times x plus 2 times x minus y equals 0. Now that's just from the partial derivative with respect to x. This is fantastic progress. Because what have we come to our conclusion? Well, it says, look, there's two possibilities. X might be negative 2, or, of course, x might be y. Those are the only two ways we can get 0. All right, well, let's keep probing. So we need to explore our possibilities. So let's explore the possibility x equals negative 2. So what do we mean by explore the possibility? Well, that means we'll plug in negative 2 into f sub y, and we'll see what we get. So what happens? Well, we're going to get minus 4 plus 8 plus y squared minus 5 equals 0. And now we say, well, this is great. Because really, what does that say? I have minus 9 plus 8 plus y squared to be 0. That can only happen if y squared is 1, which says y is plus or minus 1. You want to make sure you get all of the critical points, and you definitely want to make sure you don't get any extras. Extra critical points are bad here. because if you go to classify them, you're like, oh, I got all these mins and maxes which don't even exist as mins and maxes. Ah, terrible, terrible. Okay, so, but we've gotten two possible values for y. There's that value for x that goes with it. So we got -2, 1, and -2, -1. Okay, good. 2 critical points so far, because we only went down one of our branches. Now to go down the other one. Let's see what we get. If we say x equals y, okay, well, I can replace, well, look, I'll just replace y by x. That might be easier. So minus x squared minus 4x, and then plus x squared minus 5 equals 0. Well, the x squareds cancel off. Ha ha. Nice. Okay, well, since the x squareds cancel, what's left? Well, we can say, hey, that's the same as 4x is equal to -5, because I can move the 4x across, or x equals -5/4. Now, we know x equals y, so that leads us to the point -5/4, -5/4. And there we go. We've got 1, 2, 3 critical points. 3 critical points. All right. Well, woohoo. Good. We've made beautiful, beautiful progress. But, of course, we're not done, because we've only done the find. Next up, got to do some classify. So, on to stage 2, classification. So let's go through this. f, x, x. So that would be 4x plus 4 minus 2y. f, y, y. 2y. All right, that looks pretty promising. f, x, y. Okay, that would be minus 2x and minus 4. Now you can always check fxy by also doing fyx. So in other words, come here and take derivative with respect to x, minus 2x minus 4. Yeah, good, they match. So our discriminant, which is fxx, fyy, minus fxy quantity squared, is really, okay, 4x plus 4 minus 2y times 2y minus 2x minus 4 squared. All right. Well, let's begin. So, we'll plug in our points. -2, 1. Now, when we plug in minus 2, see, minus 2 times minus 2 is 4. 4 minus 4 is 0. So that last term goes away. Well, that's going to be nice. Of course, what happens to the first terms? Well, we get minus 2 times 4 is 8 plus 4. That's minus 8 plus 4 plus 4 is 0. So we're going to get 0 times, well, 2 times 1 is 2. And then we're going to subtract 0 squared, which is 0. Well, what do we do? The answer is, it is what it is, right? Inconclusive, inconclusive. Now, what happens if you plug in minus 2 minus 1? All right, does that make any difference? Well, what happens there? Well, we're going to have a minus 4, and then we're going to have a plus 4, and, right? Oh, sorry, excuse me, minus 8 plus 4 plus 2. Did I compute this first one right? I want to go back and check it. So minus 8. I did not do that right. I am so sorry. Okay, let's do this carefully. Once you make one mistake, it's kind of like, almost like an infection, right? Once you make one mistake, they just sort of start to multiply. So it's like, no, bring it under control, relax. We know how to handle it. It's just focus. Okay, minus 2 times 4 is minus 8, plus 4 minus 2. So it's minus 8 plus 4 minus 2. We'll fix that up in a second. 2 times 1 is 2. And then it is 4 minus 4 is 0. Okay. Now, good news. We don't get 0. We really don't want to get 0. Because 0 is like, I don't know. And it just feels terrible when you don't know. But here, what happens? You see, you're going to get minus 10. And then you're going to get plus 4. It's negative 6. So it's a negative quantity. It's a positive quantity. So the whole thing is negative. So that says, look, saddle, saddle. All right, good. How about minus 2 minus 1? Well, okay, that's minus 8 and plus 4 and then plus 2. And now we're going to multiply it 2 times minus 1. That's minus 2. And then subtract. Well, minus 2 times minus 2 is 4 minus 4 is 0. So what do you see here? We have minus 8 plus 4 plus 2 is minus 2 times minus 2. It's positive. Ah, great. It's positive, and look at the sign. It's negative for the FYY. So, since FYY is negative 2, which is negative, that says this has to be a local max. All right, good. Now, one more point. This one will be the interesting one. Let's see what happens. Negative 5/4, negative 5/4. Okay, so, well, negative 5/4 times 4, that's minus 5, plus 4, and minus 2 times minus 5/4 is minus 5/2. Then we multiply it by minus 5/2. And then, over here, we're going to get subtract. Minus 2 times minus 5/4 is going to be a positive 5/2, and subtract 4 squared. Okay, well, let's, well, be careful, right? That's a good piece of advice. We like it when we're careful. So if we're careful here, negative 5 plus 4 is minus 1. And now we take minus 1, subtract 5/2. That's really minus 7/2. And here we have minus 5/2. Now, 5/2 minus 4 is the same as 5/2 minus 8/2, which makes it negative 3/2 squared. And now we say, okay, great. Now we can see the sign. This is positive 35/4. Subtract 9/4. And so what do we see? 35 is bigger than 9. So this is a positive quantity. All right. Well, if that's positive, then we say, well, let's look at one of these things. We can look at FYY. That's negative 5/2, which is negative. And therefore, we say, aha, a local max. Good. So we have 2 local maxes and 1 saddle. So let's put it all together somewhere. I'll put it all together up here, right? So we have negative 2, 1 is a saddle. And then we have minus 2 minus 1. And this other point here, negative 5/4, negative 5/4, these are both local max. And so there we go. Aha, done. Well, it's a process, right? You just have to be careful, be patient, and see what happens. All right, good. Well, let's keep going. More problems to do. All right, on to our next problem. Ooh, it's the find and classify. We already knew it was going to be that. Find and classify the critical points of 2x squared y minus 2xy plus xy squared minus y squared plus 4/3 x cubed minus a half x squared minus 6x. Woo! Interesting. Well, let's begin. It's pretty much better than not beginning, right? So we've got to do something. So we start with our partial derivatives. F sub x. Take rid of everything with respect to x. 4xy minus 2y plus y squared plus 4x squared and minus x and minus 6. Oh my goodness. Oh wow. Woo. That is a lot of stuff there. A lot of stuff. Well, let's hope the other one is a little bit simpler. Okay, f sub y. Let's see what that gives us. Well, that would be 2x squared and minus 2x, and here plus 2xy minus 2y, and okay, that's it. All right, well, that is definitely simpler. So let's focus our energy on our f sub y. It looks like it might factor. If we think of grouping, so, problems they like to hang out in groups. You like to hang out with things which are very similar to you. So, for example, here, you can factor out a 2x. That would be x minus 1. And here you could factor out a 2y. If you did that, you'd be left with x minus 1. So, this becomes 2 times x minus 1 times x plus y equals 0. All right, well, that's a lot simpler, right? It becomes nice and compact, and we can see right away, hey, there's two possibilities. It might be that x equals 1, or it could be that x equals negative y. So let's explore these two avenues. Let's start with the first x equals 1. Okay, so what would happen? So for that, we say, okay, let's take x equals 1 and come back into our first equation. So everywhere we see an x, we're going to replace it by 1. So we would have 4y, all right, minus 2y plus y squared, right? And then plus 4 minus 1 minus 6 equals 0. Okay, so if we clean it up a little bit, what do we have? We have y squared, 4y minus 2y plus 2y, and then 4 minus 1 minus 6 would be negative 3. All right, so now the question. Can we find two numbers that multiply together to give negative 3, but when we combine them by adding, we get positive 2? Well, there's not a lot of ways to get 3, right? So it's 3 and 1. Like, oh, plus 3 minus 1. So this factors nicely, almost as if they had planned it, because they planned it. They always plan it. When we talk about find and classify, we never take, okay, somebody give me a suggestion from the audience. No. These are finely crafted, raised to produce a wonderful, beautiful answer. And you can check, of course, that you get 3y minus y is 2y, and 3 times minus 1 is minus 3. So, okay, so y is negative 3, or it's positive 1. But remember, we are in the place where x equals 1. So that gives us 2 points, 1, 1, and 1, negative 3. All right, so far we have 2 points, but we've only gone down one of our paths. We've gone down the first path, we've got to go down the second path. So down the second path we go. What if x were negative y? Okay, what would happen there? So we're going to go, again, similar process, but everywhere where we see an x, let's replace it by negative y. So we're going to have minus 4y squared. All right. Then we're going to have minus 2y. That just stays as it is. Y squared stays as it is. 4x squared, well, that becomes 4y squared. Of course, if you square negative y, it's the same as squaring just y. And then minus x, well, that becomes plus y at minus 6 equals 0. Okay, so the 4y squareds cancel. That's pretty nice. So what do we end up with? We end up with y squared minus y minus 6 equals 0. Well, all right. Does that factor? We need two numbers that multiply together to give us negative 6 and add to give negative 1. Wow, if these factored, this would be a beautiful problem. I think it's a beautiful problem. Okay, because it does factor. Can you see it? It's going to be y minus 3, y plus 2. Because you can check. You get y squared, good. Plus 2y minus 3y is minus y, and minus 6. So that says, hey, y is 3, or it's negative 2. And remember, x is the negative of y. So if y equals 3, then x would be negative 3. So negative 3 comma 3. And if y equals negative 2, x would be minus 2, which is positive 2. So there we go. So we have 4 critical points. 4 of them. Beautiful. Well, and they're actually amazingly nice critical points. In other words, everything's whole numbers, no crazy outliers. You know, it's maybe not the first points that you would think of, but they're all there. Great. Well, now we're ready to move. We've done the find. Time to do our classify. So, we'll block that off. And we have to write down our fxx. Okay, there's going to be a lot of stuff still, right? There's a 4y and nothing, 8x and minus 1. Our fyy, okay, nothing, that'll be a 2x and a minus 2. Okay, all right, that's fine. And our fxy, well, let's do fyx maybe. That seems like it's a little bit shorter. Taking derivative of fy with respect to x, that's 4x minus 2 and plus 2y. Okay, good, great. So there we have our second order partial derivatives, and we're going to compute this term, right? fxx fyy minus fxy squared. So 4y plus 8x minus 1 times 2x minus 2. Subtract this last piece. 4x minus 2 plus 2y squared. All right, well, 4 points to check, and just be patient. And if we can do that, we're great. So let's start. When we plug in 1, 1. Well, that's a great choice. Easy to do it when everything's 1. 4 plus 8 minus 1. 11. 2 minus 2. 0. Very not promising. Subtract. 4 minus 2 plus 2. Well, that's 4 squared. So 11 times 0, subtract 4 squared. Definitely a negative value. So our conclusion is that 1, 1 is a saddle. All right, that's perfectly fine. What happens if we plug in 1, negative 3? Okay, so let's be careful here. Wherever we see an x, we put a 1, or we see a y, we put a negative 3. So negative 12 minus 1, that's minus 13, plus 8. So put that together, we're going to get negative 5. Okay, now x is still 1. 2 minus 2, 0. Well, minus, here, we're going to have 4 times 1, 4, minus 2 is 2, and then minus 6, right? Because that's 2 times negative 3. And so 4 minus 2 minus 6 is negative 4 squared. Aha! And negative 4 squared, it's the same as 4 squared, because the square gets rid of the negative. So, and the 0, so it's 0 minus 16, still negative. So this point, 1, negative 3, is also a saddle point. Okay, all right, well, that happens. No problem, no problem. We keep going. So, let's try our next point. Negative 3, positive 3. Okay, so where we see an x, we put a negative 3. Where we see a y, we put a positive 3. So we'll get 12 minus 24. That's negative 12. And then minus 1 more. So that would be negative 13. Then we're going to get minus 6 times minus 2. Minus 8. Subtract. Okay, so 4 times minus 3 is minus 12. Minus 2 makes minus 14. Plus 6 would make that minus 8. And of course, we're going to square that. Now, we don't need to know the value. We just need to know the sign. Which one's bigger? Well, the 13 and 8, we can ignore the negatives because 2 negatives make it positive. 13 times 8 versus 8 times 8. Well, 13 times 8 is bigger. So this is positive. And we see, aha, the fxx and fyy are both negative. So the fact that we got a positive out for this discriminant d, the fact that our two partial derivatives are both negative, second order partial derivatives are both negative, we put that together and we say this is going to be a local max. All right, great. One more to go. So, d2, negative 2. Well, what happens? So, I'm going to replace y by negative 2 and x by positive 2. So we have minus 8 plus 16. That's just 8. And then minus 1. All right? So, minus 8 plus 16 minus 1. 7. Yeah? Yeah. Good. Now, 2 times x minus 2. So, we're going to take 2 times 2. That's 4. Minus 2 is 2. So, 7 times 2. Subtract. Okay. 4 times 2 is 8. Subtract 2. That's 6. Subtract 4 more is 2. So we're going to subtract 2 squared. And that's 14 minus 4. That's positive. But look, these terms here, this fxx and fyy, are both positive. Okay, well, what does that tell us? Well, it tells us, hey, this says that this point here, 2, negative 2, is a local min. And there we go. We have 2 saddle points, 1 local max, 1 local min. Wow, what a problem. What a problem. This is an amazing, amazing answer. Just everything comes out so nicely. I mean, there's a lot of details, don't get me wrong. And I hope I didn't make any mistakes. I'm pretty sure we were careful. But that it comes out in the end so clean. Problems like this, they're what keep me going in math. Because it's so beautiful. So beautiful. All right. Well, okay. We can't just sit around staring at beautiful equations all day. People might think we're weird. Ha! Weird mathematicians. Who ever heard of that? Well, let's try another problem. All right. Find and classify all the critical points for this function. Whew, this looks like a really good cool down after the last couple of ones, right? Our function is 2x squared times y minus xy squared minus 2x squared plus x plus 8. All right, well, let's begin and let's find out where we end up. So, as always, because it's the same for today, take our partial derivative, set them equal to 0. So partial derivative with respect to x, 4xy minus y squared minus 4x plus 1 equals 0. Okay, well, there's a lot of stuff going on there. Let's take a look at our other partial derivative, though, right? We have two of them. H sub y, 2x squared minus 2xy. And that's it. Like, whoa, that one looks a lot nicer. Okay, so we're going to focus on the h sub y. Notice we can factor, because they both have a 2x, and then you're left with an x minus y equals 0. So we get two possibilities, namely the x equals 0 or the x equals y. Well, we got to check both, because there might be solutions in both. We don't know. We have to find out. Now, if x equals 0, so we used h sub y, so we're going to go into hx. Everything with an x goes away. We get minus y squared plus 1 equals 0, which really says y squared equals 1, or y equals plus or minus 1. Be careful with your squares, right? If you have something squared equals a number, when you're solving, plus or minus. Well, this is great. So what do we end up with? We end up with two possibilities, 0, 1, and 0, negative 1. Wonderful. Two critical points. And they're both so clean. It just warms your heart. Okay, well, that's our first path, but we got to try our second path. So let's do that one next. All right, so now we're supposing x equals y. What happens? What happens? Well, again, we come back up here. I'll replace y by x. So we'd have 4x squared minus x squared minus 4x plus 1 equals 0. Or if you like, 3x squared minus 4x plus 1 equals 0. Now, does this factor? And it will factor. I have faith in it. You might be a little bit skeptical, but don't be too skeptical. The thing that throws us off is it's kind of flipped around, right? So normally we're used to like a 1x squared minus 4x plus 3. And if we saw that, we'd be like, aha, it's going to factor. But we can sort of say that it's the same process. We just have to say, now we get numbers attached to the x. In fact, if it did factor, there's not a lot of choices, because there's not a lot of ways to write 3. It's 3 times 1. And so it would have to, if it did factor at all, 3x and x, and the 1, only one way to write 1 is 1 times 1. The fact that there's a minus here and that positive there, so minus 4x, positive 1, so if it factored at all, it would have to factor like that. Does it work? 3x squared minus 3x minus x. That is minus 4x and then plus 1. Nice. Okay, so what does that lead us to? Well, we get x equals 1/3 or x equals 1. Okay, but remember x equals y, so that gets to the points 1/3, 1/3, and the 1, 1. Perfect, perfect. So there are 4 critical points. And we're done with the find. Transitioning smoothly. We're going to go right into looking for classifying. So, second derivatives, hxx. So, we have 4y minus 4. hyy minus 2x. All right, that's pretty good. Hxy. So if I come to hx, take derivative with respect to y, we'd have 4x minus 2y. So we're interested in what happens to this expression, d, which is our hxx, hyy, minus hxy squared. Okay, so that's 4y minus 4 times minus 2x, subtract 4x minus 2y squared. And now we test every single point. Okay, so when we plug in 0, 1, everywhere where we see an x, we're going to get a 0. Look, that knocks out the first term, right? Because there's an x right there. Gone. 0 minus, and we have 0 minus 2 squared. So 0 minus 2 squared, right? Well, that's a negative value. So that says 0, 1 is a saddle. All right. What if you plug in 0 minus 1? Well, look, 0 again. Boom, that knocks that term out. Gone. Gone. Wow. Whew, never had a chance. Okay, subtract. Now you're going to get 4 times 0 is 0. Minus 2 times minus 1 is a positive 2 squared. Still less than 0. And so 0 minus 1 is also a saddle. All right. Well, still two possibilities. Let's do 1, 1. We'll say the fractions for the end. If we plug in x equals 1, y equals 1, well, 4 minus 4, 0. Gone. Wow. Forget it. Forget it. Oh, terrible. Subtract, and then we're going to get 4 minus 2 squared. So that's 2 squared, less than 0. Okay, so 1, 1 is a saddle. All right, well, it could be all saddles. It's okay. It's okay. It's quite possible. But it's nice if you have at least one point that's not a saddle. So our last chance. You are our last hope. Well, no pressure, no pressure. Okay, so 4 times a third minus 4. That's 4 thirds minus 4. And if you're careful, okay, 4 thirds subtract 4 becomes 4 thirds subtract 12 thirds, which makes this minus 8 thirds. Okay, that's promising. Minus 2 times a third is minus 2 thirds. All right. Subtract. And now we get 4 thirds subtract 2 thirds. Well, that's going to be 2 thirds squared. And when you see, we get 16 ninths, subtract 4 ninths. But we can see, okay, look, clearly the first term is bigger in value. It's positive minus positive, right? 16 ninths minus 4 ninths means this whole thing is positive. And the partial derivatives are hxx and hyy are both negative. So when we see the partial derivatives are negative and the discriminant is positive, when I say partial, second order partial derivatives with respect to x or second order partial derivatives with respect to y, that says, hey, this point, this is a little bit more interesting. It's a local min. And there we go. All right. Done. Done. Whew. 1/3, 1/3. Coming in at the last minute, the 11th hour, to make it slightly more interesting. And that's always nice. Always nice. Good. Well, we continue to our next problem. All right. Ah, they keep coming. Well, that's all right. We're getting better at this, right? I hope so. We should start picking up the flow of these problems. Find and classify all the critical points for this function. X to the fourth minus 2x squared y squared plus y to the fourth plus 8 thirds y cubed minus 16y squared. Wow. All right. Great. Let's see what happens. Same process, right? Set the partial derivatives equal to 0. 2 equations, 2 unknowns. Life is good. 4x cubed minus 4x y squared, nothing, nothing, nothing. Wow, that's beautiful. That's really beautiful. Good. Well, we're going to come back to that one. How about f sub y? Well, what does that be? That goes away. We're going to get minus 4x squared y. Then we're going to get plus 4y cubed plus 8y squared. And then minus 32y. And we're going to set that equal to 0. All right, great. Well, interesting. Well, let's get going. Now, I would say that between these two, if I had to pick, and I kind of have to pick at some point, which one to start working with, I want to work with the simpler one, which means the f sub x. So, because you see there's only two terms, and we can already spot they have terms in common. So, say, look, that says 4x times x squared minus y squared equals 0. All right. Wow. Great. So what does that tell us? Well, notice here, the only place where you have x, it only happens one time, and it happens to be an x squared. So that says we could replace the x squared by y squared. Ah, that's cool. That's cool. Good stuff. Good stuff. All right, so let's split it now into two possibilities, right? Because what are our possibilities? Well, we of course have the x equals 0 possibility, and then we have the x squared equals y squared possibility. All right, so let's start. I think the x equals 0 possibility track should be pretty straightforward because, well, maybe not. You never know. When x equals 0, coming here, it just says the first term goes away. Wow. Well, now we get a cubic. So, 4y cubed plus 8y squared minus 32y equals 0. Well, that's all right. Not to be disheartened. It's a cubic, but there's at least one factoring we can do. They all have a y. They're also all multiples of 4. So we could pull out a 4y. So that'll become y squared plus 2y minus 8 equals 0. And now we say, well, can we factor that quadratic? What would we need? We'd need to have two numbers that multiplied together to give negative 8, but added together to give positive 2. Can we think of two numbers that do that? Yeah, 4 and negative 2 do that, right? Let's check that. So we're thinking y plus 4, y minus 2. Okay, let's check. Y squared, good. Minus 2y plus 4y is 2y minus 8. Wow. They set it up nicely for us. So what are the possibilities? Well, there's a couple. Y equals 0, negative 4, or positive 2. Right? 0, negative 4, positive 2. And remember, x equals 0. We're on the x equals 0 track. So that gives us a bunch of points. 0, 0, 0, negative 4, and 0, 2. So we're already up to 3, and we've only gone down one track. We've still got this whole other part to do. Hoo-hoo! Cool. All right. Well, let's continue. So going down the other way. X squared equals y squared. Now, notice we already observed, look, there's only, x only shows up as one place, as x squared. So if we replace x squared by y squared, we say, well, look, that becomes minus 4y cubed plus 4y cubed plus 8y squared minus 32y equals 0. And now, almost as if it had been planned, because I think it was planned, they cancel. We say, well, that really makes things nice. What ends up happening next? Well, okay, what happens next here is we can factor. There's only two terms left. They both have factors of 8 and y. So that factors into 8y times y minus 32. Okay, so, and equals, whoops, did not factor that correctly, right? Because I pulled the 8 out, that would be just a 4 left. Okay, so that's supposed to be a 4 there. We're among friends. Okay, so what happens? Well, you get y equals 0 or y equals 4. Now, suppose y equals 0. What happens next? Well, if y equals 0, that says, hey, x squared has to equal 0 because 0 is squared. So that gets us to the place that x is plus or minus 0. Plus or minus 0. That just means 0. So that gets us to the number 0, 0. Wow, that point is so critical, it's critical twice. It's extra critical. Well, no, that's a nonsense thing. What does it mean to be extra critical? Come on. Let's not be silly. All right, well, now how about here? Y equals 4. That says what? X squared equals y squared. So x squared equals 16. So what does that say about x? It's 4 or negative 4, right? So really we get two possibilities, plus or minus 4. And remember, y equals 4. So that gets us to the possibilities 4, 4, and negative 4, 4. All right. So we have a total of 5 points. We don't need to test 0, 0 twice because it's not going to change in between the two times that we test. So, all right, 5 critical points. Wow. All right. For such an easy-looking function, well, maybe a little bit more than we may have expected, but, well, who knows? You don't know until you do the work. So, f(x)(x), building up our second-order derivatives, that would be 12x squared minus 4y squared. All right. Fyy. Ooh, this one's going to be here for a while. We're going to have minus 4x squared plus 12y squared plus 16y minus 32. There's a lot of y's in this problem. Never mind the whys and wherefores, right? Just be patient. Fxy, well, good news, there's just one. Right? When we take f sub x, there's only one place where the y shows up. So we end up with minus 8 times x times y. All right. Well, now, what's going to happen? Well, that's a great question. We got to test all these points. And the way we test, of course, is we plug it into this expression, d, which is our fxx, fyy, minus fxy squared. Okay. 12x squared minus 4y squared. Well, that'll be one of them, times this minus 4x squared plus 12y squared plus 16y minus 32. Okay, all right. Subtract minus 8 times x times y squared. All right, well, here we go. 0, 0. Now, what happens? Well, the nice thing about 0, 0 is it's really easy to compute. Everything with an x or y becomes 0. So 0, 0, 0, 0, 0, minus 32. So you get a 0 times a minus 32. Subtract 0 squared. So subtract 0 squared. And our grand conclusion, this is equal to 0, which means we stop. It's inconclusive. And we don't have the tools to figure out what's going on. And in particular, we'd have to stop and say, okay, well, what's really happening? What's really happening as we go in different directions? We could actually answer the question. It's not that hard if we say look along different axes. I believe if, for example, if you look along, okay, so this is an inconclusive, and we're going to just ramble for a few minutes here saying if it's inconclusive, one of the things you could do is, if you really, really, really had to know, is say, well, let's look along the different axes and see, can we understand the behavior? So what would happen? If we went along x equals 0, what would happen? Well, you get 0, 0, and then you get this expression. Well, y to the 4th plus 8/3 y cubed minus 16y squared. And if you ran your second derivative test in calculus on this one, you'd see, oh, see, the minus 16y squared is the dominant term near 0. And so this would be a max. So this is a max along the y-axis. Okay. On the other hand, if you put in y equals 0, well, what do you get? Lots of zeros. It looks like x to the 4th. And now that's easy to spot. X to the 4th, that says, hey, this looks like a min along the x-axis. And now we're like, okay, forget it. It's not a local max, it's not a local min. It is a saddle. But that does not come from the second partials test. That came from saying, hey, let's look in some slices and see behavior. Looking at slices can be dangerous. It's a perfectly fine way to spot a saddle. It basically is useless to spot local mins and local maxes. We didn't need to do that, by the way. So that was all bonus. Good for us. Bonus! But back to our regularly scheduled problem. Okay, so where were we? Oh, yeah, 0, 4. Negative 4, sorry. 0, negative 4. So just have to be careful here. Everywhere where we see x gets a 0 and y gets a negative 4. So negative 4 times 4 times 4. Wow, that's a negative 64. And here we're going to get a 0. 12 times 16. Really? Really? Wow. Okay. Well, 12 times 16 is a number. 192. 192, I think, because it's 120 plus 9. Yeah, 192. And then we're going to get 16 times negative 4. That's minus 64 minus 32. Subtract 0 squared. Okay, phew. At least that's easy. But here we say, look, great, beautiful actually. Because what's going to happen? It's going to happen that, you see, we have a negative value times a positive value, which makes it negative. So this is negative. All right, so this is a saddle. Good. Another saddle, actually. Okay, how about 0, 2? Well, okay, where we're seeing x, we get a 0, so it's 0. 4 times 4 is 16, negative 16. And 0. 12 times 4, 48. And then we have 16 times 2 plus 32 minus 32. And subtract 0 squared. But we can see that's a positive, that's a negative. Positive times negative, well, that's going to make the whole thing negative. So also a saddle. Wow. So far, 3 for 3 are saddles. Well, could be all saddles. It's possible. Can't rule it out. Not yet. Okay, well, 4, 4. Okay, all right. What happens? Well, 12 times 4 squared minus 4 times 4 squared. All right. Well, really, it's 8 times 4 squared, right? Because you can factor it out. All right, so that's 8 times 16. That's 128. So positive 128. And then, well, we're going to get minus 4 times 4 squared. All right, that's minus 64. 12 times 4 squared. All right, that's 12 times 16, which is 192. At least that's what we said it was a few minutes ago. I don't think it's changed in the last few minutes. And then we're going to get 16 times 4 is 64, and minus 32. And then we're going to subtract minus 8 times 4 times 4 squared. All right, wow. Okay, these are some big numbers we're working with here. But, all right, we can clean it up. 64 and 64 cancel. 192 subtract 32 would make this 128 times 160. Now, 8 times 4 times 4. What is that? Well, 8 times 4 is 32, times 4 more makes 128. So subtract 128 squared, which is 128 times 128. And now we're like, aha, aha, aha. We don't care about the value, we care about the sign. And if we compare, see, look, because the 128's matched, and the 160 beats 128, this whole thing is positive. And these terms here are both positive, which means that this is a local min. Good. So we've had saddle, 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 local min. One more to go. When we plug in negative 4, comma 4, okay, what will happen? Well, we're still going to get the same kind of thing going on here. 12 times 16 minus 4 times 16. And we worked that out. Still 128. Nothing happens on that term. And here, the first two terms, still the same, because the squaring is going to get rid of pretty much everything. Negative 64 plus 192. And now, it's still, in fact, the y terms is still the same. And plus 64 minus 32. See, the only places that really change is that place right there. So it's going to change this to a positive 8 times 4 times 4. But look, because we're squaring, it doesn't make any difference at all. And so it's going to still be positive. And these terms are still 128 and 160, and therefore also a local min. So we get 2 saddles for 3, if we include that inconclusive ones, and 2 local mins. Whew, wow. This one, for not looking so harmless, it kind of got a little bit at the end. But, okay, phew, we made it, right? We made it. So we keep going. Keep going. Well, on to our next problem. Find and classify the critical points for the function x cubed minus 8xy plus 2y squared minus 3x plus 4y minus 23. All right, well, let's start. All right, fx, 3x squared minus 8y minus 3 equals 0. Fy minus 8x plus 4y plus 4. Oh, wow. Oh, that's so much cleaner. Wow, this is the one we've been waiting for, right? Okay, well, what can we do? We can substitute. Because you see, I can solve for x or for y. It's probably easiest to solve for y. And notice this is as an 8y. So if we really wanted to, we could say, look, if we double this, minus 16x, and then plus 8y, plus 8 equals 0. And then if we move this across, we could say, look, minus 8y is really minus 16x plus 8. So we can now replace minus 8y by minus 16x plus 8. So we say, okay, so that would be 3x squared minus 16x plus 8 minus 3 makes plus 5 equals 0. All right, well, that's looking pretty promising. Does it factor? It actually will. And you see, look, there's not a lot of ways to break up 3. 3 and 1. Similarly, 5. 5 and 1. So, because we need to get up to 16, the 3 and the 5 will multiply together. So we'll put those there. And then the 1s will multiply together. And then if we make them both minus, this should work. 3x squared, good. Minus 15x minus x is minus 16x, and plus 5. So that leads us to two possibilities, x equals 1/3 or x equals 5. All right. Now, what about y? Well, come back. Look, divide both sides by -8, and we get y equals 2x minus 1. That's what it turns out to be. So, okay, well, wonderful. If y equals 2x minus 1, then we can put these in. So, if x equals 5, 2 times 5 is 10, minus 1 is 9. So, that gets us to the point 5, 9. And here, 2 times 1/3 is 2/3. Subtract 1 would get us to the point 1/3 minus 1/3. So there's two critical points. Wow, that was great. Okay, well, we're not done yet. What comes next? All right, fxx. Whoops, there we go. Oh, that looks terrible. Let's try this again. fxx, 6x. fyy, 4. Ah, nice. fxy is -8. So d, which is fxx fyy minus fxy squared, that will become 6x times 4 minus -8 squared. That's wonderful. And it's interesting here, there's not even a y involved. So when we plug in, we really have to say it comes down to what's happening with the x, right? Okay, so 6 times 1/3 is 2. Times 4 is 8. And we're going to subtract 64. So this is 8 subtract 64. Well, that's very negative. And so our conclusion is 1/3 minus 1/3 is a saddle. And there we go. How about 5, 9? Well, 6 times 5 is 30. 30 times 4 is 120. All right, well, that's a lot bigger. Subtract 64, 120 subtract 64. Well, that's a positive number. Nice. And notice our fyy is 4, which is positive, and therefore this 0.59 is a local min. Because remember our basic rule, positive number means our curve looks locally like a smile. And a negative number means locally we look like a frown. So we're positive local min. And done. Now I know what you're thinking. We need more problems like this one. I don't know about that. I think there's value in having fun and doing challenging problems. In fact, there's more value because the more challenging, yeah, sure, we can make mistakes, but it's through pushing through and thinking, how can we solve for things? It's a better puzzle, and we like solving puzzles. All right. One more problem. Let's do one last one to finish this up. We've had a lot of fun, and let's see if we can't finish on a good positive note. Find and classify the critical points for the function x to the fourth minus 4xy minus 7x squared plus 4y squared plus 4x minus 8y plus 20. All right, well, let's jump in, right? Absolutely. So what do? We start with our partial derivatives. 4x cubed minus 4y minus 14x plus 4. All right. Not so clear what's going on there. Let's try g sub y. Maybe there's better news there. Minus 4x plus 8y and minus 8 equals 0. Now that does look more promising. And in particular, we say, whoa, hey, we could solve for x or solve for y looking ahead, right? Because we want to look ahead. We could say, there's only a single y there. So maybe let's try to replace the y by x. So let's note this is the same as minus 2x plus 4y minus 4 equals 0. I'm dividing everything by 2, 2, 2, right? And then we move the minus 4y across. So this says minus 4y is equal to minus 2x minus 4. All right. So we can replace the minus 4y up here. So we get 4x cubed plus minus 2x minus 4 minus 14x plus 4 equals 0. And now we're like, whoa, this is a cubic. But then we're like, whoa, look at the minus 4 and the plus 4. Almost as if somebody had planned for it to be nice, because somebody did. So we have 4x cubed minus 2x minus 14x makes minus 16x equals 0. And now we're like, wow, amazing, amazing. This is factoring because we can pull out the 4x. And we're like, x squared minus 16. Cool. This goes even further. This becomes x minus 4, x plus 4 equals 0. And now we're like, wow, wow. This is really good. Because this says there's 3 possibilities, 0, 4, or negative 4. Oh, where are you coming from? Okay, 0, 4, or negative 4 for the x. Now, what is the y? Well, okay, we should clean this up. If we divide by negative 4, we can say, look, y is really what? Well, minus 2x minus 4 over negative 4. But that simplifies. That's the same as saying y equals, factor out minus 2 from top and bottom, x plus 2 over 2. So there we go. Y is x plus 2 over 2. So let's figure out our coordinates. 0, okay, 0 plus 2 over 2 makes 1. 4 plus 2 is 6 over 2 makes 3. All right, and let's see. Just checking here. I feel like I've made a small mistake somewhere. Where have I missed something? Well, no. All right. Well, keep going. Right. No. There was a mistake. Do you see it? Aha! I see it. You're probably like, oh, Steve, you silly guy. You forgot to factor out the 4 properly. See, I was so excited because it was like, perfect square. I was like, well, wait a second. See, if I factor 4 out of 16, it should have been a 4 here. So this should have been a 2 and a 2. And this should have been a 2 and a minus 2. There we go. Okay, so that was still correct. And, okay, so 0, 1 is perfectly fine, right? Because that's not affected. But we'll list them again. 0, 1. Then 2 plus 2 over 2. That's 4 over 2, which makes it 2. And then when we plug in negative 2 plus 2 is 0 over 2 makes 0. So those are our 3 critical points. 0, 1, 2, 2, minus 2, 0. Can't believe it. Man, and it's the last one, of course, too. Well, all right, back to our problem. Now, switching into classification. So we need to have our derivatives. Gxx, 12x squared, and minus 14. Gyy, well, 8. That's pretty easy. Gxy, negative 4. Wow, also pretty easy. So our function, gxx, gyy, minus gxy squared, well, 12x squared minus 14 times 8, subtract, negative 4 squared. All right, so here we go. Plug in 0, 1. Well, 0 squared is 0, so we get minus 14 times 8, subtract minus 4 squared. Oh, look, that's really subtract 16, right? We can do that. But the thing is, we can spot that's negative. So our discriminant is negative, which means this is a saddle. There we go. All right, good. Saddle point. Nice. Well, let's do another point. The tutu. Okay. Well, what happens with our tutu? When we plug in 2, we're going to get 12 times 2 squared. All right. 12 times 4, 48. 48 subtract 14 is, well, it's a number, right? 34. So it's 34. And then we're going to times it by 8 and subtract 16. Well, what's true? It's positive, right? Yeah, it's positive. And we see, aha, our GYY, which is 8, is positive, which means that this point is a local min. And finally, negative 2, comma 0. Well, what's going to happen here? Well, the good news is, look, there's no y involved in our term. The only place is x, and the only x is an x squared. So it turns out it's still the same computation. 34 times 8 subtract 16, which is positive. GYY is still 8, which is positive, which means, aha, also a local min. And there we go. Done. Done. Other than that silly error, not so bad. Now this problem, I actually am very proud of this one. I wrote this one. It's not the one I'm most proud of. There are some other ones that I wrote. In fact, a lot of the ones we did today are ones I came up with. Nothing really special about them. There's lots of different ones out there. But this one I put on an old final. And then the next semester I wasn't teaching the class. They used it again. And then a year later, they used it a third time. So this problem is so nice, they used it thrice on the final exam. And you'd say, wow, surely by the time they used it the third time, the students would be totally ready for it. I don't think they were. You know, the thing is, there's not that much out there. I mean, it sometimes feels overwhelming. It's like, oh, there's so much math out there. But actually, the ideas are very similar. As you start looking over problems, you're like, whoa, there's patterns here. And I can learn patterns. And the more patterns I learn, the more power I have. And I can solve more and more challenging problems. And that's what we want. We want you to solve problems because, boy, we have them. There's a world full of problems, not just math problems, all sorts of problems. But you're getting there. You're going to become amazing. And I'm so proud of what you're doing. Keep it up, and I hope to see you again soon. Bye.